Let's discuss limiting reagents and the balanced chemical equation, and we use reagent and reactant as interchangeable terms. When two chemicals react, we find that there is a best mixture of moles of one to moles of the other. So here's how to find it in the lab and what it means. So our question is, would just any mixture of moles of two chemicals give a chemical reaction? We experimented with hydrogen and oxygen gases, and we know that at the same temperature and pressure, equal volumes of gases have equal numbers of molecules. So we can measure the relative volume and use that as the ratio of moles. We start with all oxygen, and then we add fuel, we add hydrogen little by little, and measure the intensity of the reaction either by the distance a rocket will fly or by the intensity of the sound that the explosion makes. Here's our setup, going from no hydrogen and 6 volumes of oxygen all the way to all hydrogen and no oxygen. And we see the average distance that's flown by the little tiny rockets that we used. We can then graph that. The distance is a function of the hydrogen ratio. Here, the optimum ratio of hydrogen to oxygen appears to be 2 to 1. As we've added hydrogen, we get to a point where the hydrogen is about 2/3 of the total volume and the oxygen about 1/3, and we seem to hit a high point. We hypothesize that this means that 2 moles of hydrogen will react exactly with 1 mole of oxygen. Now, with no hydrogen to oxidize, the oxygen molecules just bounce around when the voltage hits them, and no energy is released and the rocket does not move. After we add some hydrogen, a reaction is happening. Water is given off, energy is released, the rocket moves, and sound waves are generated. With more hydrogen, more oxygen is reacting, more energy is released, and there's more motion and sound generated. At this peak, with exactly 2 hydrogen molecules for each oxygen, we get the most sound and motion generated. As more hydrogen is added and oxygen then it becomes less and less a part of the mixture, all the oxygen is reacting, but some of the hydrogen is left over. And the reaction is generating less and less energy as we go down this line. Finally, with all hydrogen and no oxygen, there's nothing to oxidize the hydrogen, there's no reaction, and no energy of sound or motion. Our hypothesis here is good. 2 moles of hydrogen reacting exactly with 1 mole of oxygen. This explains our data and observations. We've done this experiment over and over for several years, and although the data kind of clusters all over the place, the trend lines are still looking like this. So we write the balanced chemical equation that says 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water vapor, or if you would like to call it steam. Now we interpret this. Going up the hill, it's hydrogen that is limiting the reaction. All of the oxygen is being used, but we don't have enough hydrogen to use all the oxygen. And so as we go up the hill, we add hydrogen and the reaction gets more intense. Going downhill, the oxygen is limiting and there is too much hydrogen added there. Let's now move to another reaction, the reaction of acetic acid and sodium hydrogen carbonate, which is studied with gas pressure sensors. In this reaction, an acid-base reaction, acetic acid, HCH3COO, reacts with sodium hydrogen carbonate, which is acting as a base, to form water, carbon dioxide, and sodium acetate. In the experiment, we measure the pressure of the carbon dioxide that is given off over and above atmospheric pressure as we increase the amount of acetic acid in the mixture of the two. The pressure increases as the amount of acid is increased, but the pressure stops going up after about 1.5 millimoles of acid is employed in the reaction. This is the graph that we have developed from the various data points that we have. It looks a little bit like what we saw with the hydrogen and oxygen, but not exactly the same, because here we're just adding acetic acid to a measured amount of a sodium hydrogen carbonate solution. As increasing amounts of acetic acid are added to the sodium hydrogen carbonate, the carbon dioxide production increases, and so the pressure change is higher and higher with the increasing amounts of acid. But at about 1.5 millimoles of acetic acid being added, the increase stops. And from that point on, adding more acid produces the same amount of carbon dioxide. We infer that the acetic acid is our limiting reagent as we go up this line, up until about 1.5 millimoles has been added. And at 1.5 millimoles, the acid exactly equals the sodium hydrogen carbonate. And, as you probably know already, there's 1.5 millimoles of sodium hydrogen carbonate in each one of these containers. Above 1.5 millimoles of acid, the acid is in excess and the bicarbonate is limiting. There's not enough bicarbonate to hit all the acid that's being added here, 2 millimoles, 2.5, 3. There's only 1.5 millimoles of the sodium hydrogen carbonate, so there's not enough to react with all the acid in this area. And that's why you have a flat line here. This then confirms that there is a 1-to-1 ratio of acid to base in this reaction. 1 mole of acetic acid reacts with 1 mole of sodium hydrogen carbonate to form 1 mole of water, 1 mole of carbon dioxide, and 1 mole of sodium acetate. Now, when solving problems in stoichiometry, please remember that you will always use the limiting reactant as the one on which all calculations are based. You will not use anything that's in excess to do calculations. If you are given the amounts of both reactants, then, you first have to determine the number of moles of each, and then from the balanced chemical equation, you will see which one is limiting. So we can not only get our balanced chemical equation, as we have done here with our limiting reactant studies, we can also, once we have the balanced chemical equation, solve problems by first determining what is the limiting reagent.